A hacker stole $60 million in 2016, and the people who built the system admitted they couldn't do anything to stop it. Not because they lacked skill, but because the rules they built made it impossible. That's not a failure. That's the system working exactly as designed. So what does it mean when code literally cannot be changed? To understand why, you need to see what a smart contract actually is. When a developer deploys a contract on Ethereum, the bytecode, the raw machine instructions, gets written directly into the blockchain's transaction history as a permanent record. That address, that string of hex characters, now points to frozen logic. There is no update operation, no patch command, no delete key. The Ethereum protocol simply does not have those concepts for deployed contracts. The bytecode at that address is as fixed as a transaction from 2015. It is part of the permanent ledger, not a file on a server someone can overwrite. The DAO is the textbook case. In spring 2016, a venture fund called the DAO deployed a contract on Ethereum. It raised around $150 million worth of ETH from thousands of investors. Ethereum's own core developers, the people who built and maintained the protocol, knew the contract contained a reentrancy bug. A reentrancy bug means the contract would pay out ETH before updating its internal balance, so a caller could repeatedly request withdrawals in a single transaction, draining funds like a bank ATM that dispenses cash before recording the deduction. The developers knew. But the bytecode at address 0xBB9BC244 was already mined, already immutable. They had zero ability to edit a single line. So the bug sat live and callable, baked into a public address that anyone on Earth could interact with. This is the key shift from how software normally works. In traditional software, a bug follows a predictable path. Engineers find it, push a patch, redeploy, and users get the fixed version, often without even noticing. The attack surface closes. In a smart contract, that path doesn't exist. The bug is not a defect waiting for a patch. It is a permanent property of that address, sitting in public view with no authentication required to call it. Anyone in the world at any moment can send a transaction to that address and trigger the flaw. The DAO's reentrancy bug sat live and exploitable for roughly 2 months before someone acted, not because it was hard to find, but because there was simply nothing anyone could do to close it. On June 17, 2016, the attacker acted. Using the reentrancy flaw, they called the DAO's withdraw function recursively. Each call triggered another before the balance updated, like a revolving door that never closes. In a single uninterruptible sequence, approximately 3.6 million ETH drained out. At the time, that was around $60 million. The mechanical reality is this: blockchain transactions, once confirmed, are final. Ethereum's finality means that once enough blocks pile on top of a transaction, it is mathematically irreversible at the base layer. The attacker's transactions confirmed. The ETH moved. No one could freeze the address mid-drain, no one could reverse the transfers, and no one could block the attacker's wallet after the fact because the protocol has no such command. You think 60 million in 2016 was bad? The Ronin bridge hack in March 2022 makes the stakes even clearer. Ronin was a sidechain bridge holding assets for the Axie Infinity game. An attacker compromised enough validator keys to authorize fraudulent withdrawals. Roughly 625 million in ETH and USDC left in a handful of transactions. Each transaction confirmed on-chain, each became final, and the team didn't even detect the breach for 6 days. By then, finality wasn't a technicality. It was an irreversible fact. Nothing could be clawed back at the protocol level. $625 million gone, permanent, in the ledger forever. Immutability doesn't distinguish between valid transactions and stolen ones. Confirmed is confirmed. So developers asked an obvious question. What if we build in the ability to upgrade? This is where the proxy pattern comes from. Instead of deploying one permanent contract, you deploy two. The proxy lives at a permanent address and holds all the funds and user data. The logic contract holds the actual code. When users interact with the proxy, it delegates calls to the logic contract. But crucially, an admin key controls which logic address the proxy points to. Swap the logic address and you've effectively changed the code without touching the proxy's address. Problem solved? Not quite. You've moved the risk, not eliminated it. The trade-off is exact and unavoidable. Fully immutable contracts give users a guarantee. No one, not the developer, not a regulator, not a hacker, can change the rules after deployment. The downside is that bugs are permanent. Fully upgradable contracts let developers fix bugs, but now there's an admin key. That key is a single point of human trust. If it's stolen, phished, or misused, an attacker can replace the logic contract with anything they want. Malicious code that drains all funds in one upgrade transaction. Every step toward upgradeability is a step away from trustlessness. You're not escaping the risk. You're choosing which kind of risk you prefer. If neither pure immutability nor proxy upgradeability fully solves the problem, is there any mechanism that can actually override what's on-chain? There is one, and it's extreme. A hard fork is when the network's node operators agree to run new software that rewrites the rules, including, in some cases, the state of the chain itself. The sequence goes like this. An exploit occurs, core developers propose an irregular state change, meaning a deliberate exception to the normal rules. And then every miner or validator on the network votes with their feet by choosing which software to run. If a supermajority upgrades, the new chain becomes canonical, but the minority who refuse don't disappear. They keep running the old chain, and now there are two permanent competing versions of history. The DAO hack triggered exactly this sequence. After the $60 million drain, Ethereum's core developers proposed a hard fork at block $1,120,000, a specific point in the chain's history that would move the drained ETH to a recovery contract, effectively rewinding the theft. The majority of the network agreed and upgraded. The stolen funds were returned, but roughly 10% of nodes refused on principle. They believed the chain's history should be inviolable, that code is law meant the attacker had simply used the rules as written. Those nodes kept running the original chain. That chain has a name today, Ethereum Classic. It still exists. On Ethereum Classic, the DAO theft is valid history. The attacker's balance is still there. Two permanent chains, two permanent versions of the same event, one immutable on each. Fork split a global network over ideology, created a permanent competing chain, and shook confidence in the entire ecosystem. It worked once, barely, with enormous social cost. That's why the industry doesn't treat forks as the plan. It treats them as the last resort. The practical answer is to design defenses into the contract before it ever deploys, because after deployment, your options collapse to near zero. The defense toolkit has 4 layers. First, a circuit breaker, a pause function that a trusted multisig can trigger to halt the contract if something looks wrong. Second, a time lock. Any sensitive operation, governance votes, parameter changes, upgrades, is delayed by 24 to 72 hours, so there's a window to catch and cancel malicious actions. Third, a public bug bounty to incentivize white hat researchers to find flaws before black hat attackers do. Fourth, formal verification, mathematical proofs that critical code paths behave as specified, run before deployment. MakerDAO's governance security module shows this working in practice. MakerDAO governs DAI, one of the largest decentralized stablecoins. Their core contracts include a time lock, roughly 48 hours, on all governance parameter changes. In 2023, a governance attack was attempted. A malicious proposal was submitted that would have given an attacker control over the system, but the 48-hour delay meant the proposal sat in the queue, visible and cancelable. The community detected it. They canceled it. 0 funds were lost. The time lock didn't fix the malicious proposal. It just bought time, which is precisely what immutability otherwise denies you. When a contract can't be changed, time is the only resource you have left to work with. Now step back and look at what all these mitigations actually do. Pause functions require trusting a multisig. Time locks require trusting governance participants to monitor and react. Proxy patterns require trusting whoever holds the admin key. Every single fix mechanism adds a human in the loop, which is exactly what immutability was designed to remove. This isn't a design failure. It's the fundamental tension at the core of the technology. The more fixable you make a contract, the more you are asking users to trust people rather than math. And the more you trust people, the closer you get to just using a bank. Uniswap v2 made the opposite bet deliberately. When the team deployed v2's core contracts, they included no upgrade mechanism and no admin key, no pause function, no proxy, nothing. If a bug is ever found, there is no lever to pull. That sounds reckless, but consider what it bought. Over $1 trillion in cumulative trading volume has settled through that code. No one has changed it. No one can change it. And that guarantee, the certainty that the rules will never be altered by anyone, not even Uniswap's own developers, is precisely why liquidity providers are willing to lock enormous sums into those contracts. The immutability isn't the risk they accepted. The immutability is the product. So here's where everything lands. Immutability is not a flaw someone forgot to fix. It is the foundational trade-off the entire system is built on. On one end, fully immutable contracts where no one can change the rules, trustless, but bugs live forever. On the other end, fully upgradable contracts where bugs can be patched. But an admin key exists, and whoever holds it is effectively the authority. Every real-world contract sits somewhere on that line. Every pause function, every time lock, every proxy pattern is a deliberate step toward the upgradable end. The DAO hack didn't reveal a weakness in immutability. It revealed that writing correct, permanent code is extraordinarily hard, and that the systems people build to work around immutability are themselves new attack surfaces. The question was never, can we make code unchangeable? They did that. The question is always, do we trust the code enough to leave it that way? And that turns out to be a question about humans, not machines.